is sort of complementary to what Peter and Simon have said. I guess I've used uncertainty analysis, quantification, sensitivity analysis for the last 12, 13 years. And so what I've done is some sort of general thoughts, particularly from a flight physics viewpoint, so not manufacturing, not from a financial viewpoint. And there's a very flight physics base to that. People who know me know I do lots of work on aeroelasticity. That triangle on the left is the Collar's aeroelastic triangle, which shows that everything that happens with an aircraft depends upon the inertia, so the weight, the stiffness distribution, and the aerodynamic forces. So everything from the shape that the aircraft takes in flight, through to its fuel burn, and then how it responds to things like gusts or landing loads. So that's the loads triangle, not so well known, on the right-hand side. So all of these key boxes there, the weight, the stiffness, and the aerodynamics, is all subject to uncertainties. And remember, they're all extremely coupled. So you can't take any of these in isolation, and an uncertainty or variation of one of the effects, be that through a physical phenomena, be that how you model the structure or how you design it, is going to have an effect on everything else. Okay, an equation. So Simon sort of alluded to this with his fuel burn. So that's the Breguet range equation. It's the key to everything. I mean, most of my research is looking at how do we make aircraft more efficient by exploiting the aeroelastic interactions between the aerodynamics and the structure. But at the end of the day, we're going to end up with net zero. Okay, we want to perhaps use hydrogen or batteries, but better engines, better aerodynamics, and less structural weight. Those are the key things that drive our designs. And again, there's uncertainties in all the components that help to move towards more efficient aircraft, which is one of the things, Simon's saying, at the initial concept, you've got to build or design an aeroplane that somebody wants to buy and fly. So therefore, trying to improve on range, reducing fuel burn is absolutely paramount at the minute. The certification process is very much tied in with defining mathematical models. So be it the structure, the FE, the control laws, the aerodynamics. Now remember, they are of a wide range of different fidelities. So starting from very simple aerodynamics all the way through to large eddy simulations. But the trade-off there is the amount of fidelity versus the speed. Do you then take simple structure or modeling, or do you put nonlinearities in there? So all of these yellow boxes are models. So they are developed, they are refined, they are then used in your process. The blue boxes are tests. So be they wind tunnel tests to check a new aerodynamic configuration, vibration tests there, the GBT. But there's not just uncertainty in the models, but there's also uncertainty in the tests. Talk to the people who do the tests and they'll say it's the people doing the modeling that have got it wrong, or vice versa. But even so, you've got to take into account this whole process has got uncertainty all the way through there. I guess at the end, the flight flutter tests, and at the minute that's primarily done just to validate that your aircraft is safe to fly. You wouldn't typically go and redo your models once you get to the tests at the bottom. So what I've got is 6 short examples which build upon quite nicely some of the things that Peter and Simon have been talking about. The first one here is done by Long there, so PhD student. And what we've got here is a representative aircraft wing. And what Long was trying to do was to optimize, well, either in this case, we've got a weight optimization, and we've got a range optimization, and our variables are some of the internal structure and also the amount of twist that we have on the wing. If you look at the bottom right-hand corner, well, this is showing the stress, and for the deterministic stress, the deterministic result gives an answer there which is spot on the limit. But as soon as you start putting some uncertainty, so variation in the various structural element thicknesses and also the jig-shaped twist, what you can see is in the bottom right-hand corner, let's use the cursor, is that a whole series of cases exceed the stress limit. So although if you look at the weight, the deterministic optimum is the least weight solution, and indeed it is also gives you the largest amount of range. That doesn't take into account the uncertainty. So as soon as you put the safety factor in, you find, and there's, of course, we've got different colors here, which doesn't help, but in terms of that, the optimal stress reduces directly. So this is a 1.5 safety factor, and there's also a 1.5 safety factor there on the maximum stress. So there's a big gap there. So what that is indicating, okay, just from this study, is that by taking, say, a 50% safety factor, you are making a rather inefficient structure. Now, using a robust or reliable design, what you're trying to do is minimize that tail there that exceeds, and therefore by using your uncertainty quantification techniques and then tying them in with a robust design, that enables you to produce a design which meets the criteria both in terms of your weight but also in your range optimization. So that's sort of picking up on what Peter was saying, in that, now, should you be using a safety factor that's not so big? Of course, this was just done for stress, for some load conditions, and also flutter, or that wasn't the critical case here. But it's indicating that if you use probabilistic optimization methods, you do get more efficient aircraft. Another example, just using a composite wing box, and I've used lots of things like Gaussian process, polynomial, chaos, and this is, and also surrogate modeling methods. The previous one was done using the surrogate method. And just to demonstrate that if you've got a composite wing box, but then you start changing some of the structural parameters, or say there's a plus or minus in the layer of the composite, you then get, people online, you then get a variation in here, in this case, the flutter or divergence speed. So what this sort of analysis enables you to do is to look at the effect of different uncertainties. But of course, the question is, what is the one that's most likely to occur in practice? This one's an interesting. This looks at more of the overall process. This is looking at weights, where one of the things, as I understand it, when you sell an aircraft to a customer with a certain performance, you know it has got to weigh this much. The plot on the top right-hand corner is showing, well, this is the status weight of the aircraft as it goes through from being a possibility to a concept to a design to integration and then in service. And you have this target weight, and as you can see that the status weight is above, and also this is an area where there is probabilistics used to actually try and define what is the uncertainty. And the uncertainty is not just there from all of these technical disciplines, so the materials and the loads and everything else, but also you have suppliers delivering particular components, and quite often I understand they say it's going to weigh so much, and then when it actually arrives, it's a little bit heavier, which isn't very good. So this is an area where actually figuring out what is the weight of the aircraft going to be by the time it flies, and there's a lot of work done. So this is a paper we did in collaboration with some of Simon's colleagues at Airbus, where they start looking at, well, what is the effect of the uncertainty as we go through the timeline, and can we try and figure out what are the key areas where we really do need to reduce the weight, or what are the areas that are going to be most sensitive to the actual weight. What are we doing? 10 minutes, right? Okay. A non-linear example. So this is looking at a landing gear. Shimmy is a phenomenon. You know, sometimes you're at the supermarket on the Saturday morning and you get the supermarket trolley wheel that is totally out of control and you can't steer it. Well, that's sort of okay in the supermarket, but landing at 150 miles an hour, that's not good at all. So that's a phenomenon called shimmy. It's a very non-linear interaction. The tires and the whole setup are very non-linear. And we did some work looking at using non-linear analysis and actually trying to predict bounds where, so this is the load acting on the undercarriage. This is the speed. That's the sort of like linear design envelope. But really, when by using a non-linear analysis and then tying that in with a surrogate model, we're able to say, right, in this region below the blue line, there is no LCO. Above the red line, there definitely is. But because it's a non-linear interaction, you then get regions where, depending on your boundary conditions, you may or you may not get a limit cycle. So it's not just complicated from a probabilistic uncertainty sense and what are the parameters that are most sensitive, but how do you actually then tie that in with your analysis? Totally different example here, looking at a supersonic wind tunnel model. And here the question was about looking at weight distribution of those tail elements and various other parts of the structure to try and define the flutter behavior. But by moving these masses about, and again, using a surrogate model tied in with some Monte Carlo, you start getting these variations in the natural frequencies of the structure. It's interesting enough, in some cases, you actually got mode switching, which makes life pretty complicated. But by using the probabilistic analysis, you were able to define for each Mach number not only what is the deterministic, so the green line, sorry, the black line is the deterministic speed, but then you start to get an idea of what are the range of uncertainties that you might meet. So testing in a wind tunnel at Mach 1.2 is pretty fraught with dangers. You want to make sure that the model is going to be totally secure and isn't going to fail. So this was a whole series of analysis taking into account, well, if I've got plus or minuses on my manufacturing, or can I use these weights to actually then ensure that flutter doesn't occur? And finally, when you look at, you have this thing called correlated aircraft load. So we talked about the models, but also the uncertainty is what is actually being applied. So you have a series of tests where you effectively run different lengths. So it's like going over different sizes of humpback bridges. And if you're going over a very long bridge, so like the motorway that goes at M6 over the Manchester Ship Canal, or Avonmouth in Bristol, I don't know which of the big motorway bridges, you're going up perhaps 40 meters, but you don't notice it because it takes so long. Whereas if you go over a short bridge, it's a lot of impact into the structure and you can shape the dynamics. So in the top left-hand corner there, we've got a wing root bending moment against different lengths of gusts, and you see you're getting different types of responses. And what you can do from each of those is to plot the bending moment against the torque. So sort of stuff you'll learn in first year engineering. And these responses there are put into this swarm. You then fit a big elastic band around it. That's got a convex hull. And that becomes what is known as a potato plot, or a potato plot in UK, patatas in Madrid, ouf in France, so eggs, and I believe they're called footballs in America. So anyhow, but you get this range of results. And remember, stress is not one dimensional, is it? You've got all these interactions, you can dig out more circle and other things. But what you can start to then do is then start trying to look at this in a probabilistic viewpoint. And if you look at the probability of things occurring, your potato plot on the convex hull on the top right then becomes this swarm of possibilities. And this was Irina, if you remember Irina, but she who's now at Rolls, I believe. But you can then end up with this probability of the results based again on some simulations and using some surrogate modeling. So that's just a a short series of 6 examples I just grabbed off over the last couple of days. Happy to share details of those or other work at all, but I mean, the main conclusion is that uncertainty occurs in all aspects of aircraft design, be it conceptual, preliminary, the detailed design phases. And it's not just the modeling, it's tests as well, but also things like manufacturing, the finance. I think you've still got big trade-offs between the fidelity and the speed, and particularly if you're very much at the conceptual level, how do you start making trade-offs and even make trade-offs probabilistically based on very little information? I mean, you were saying that aircraft look the same for the last 60, 70 years, but you know more or less that, okay, if I slightly make the wings a bit bigger, radar will tell you what the effect will be. You start having a blended wing body or something, we need to find, it's not just how to perhaps make better aircraft, but how to validate, how to certify them quicker. So there's uncertainty in the tests. Certainly an understanding of the uncertainties is important. How much effect do they have, but what type are they? What are the dependencies? How do they relate to other things like, say, the manufacturing? What is the best way to predict the uncertainty? But this is all helping us, I think, moving towards probabilistic certification. As I understand it, offshore structures are all developed probabilistically as opposed to the aircraft industry, which is very deterministic. So whereas we have a von Karman spectrum, which tells us what sort of gust field we're going to enter when we fly around, there's one of those for every bit of sea in the world for every month of the year. So perhaps that's something to look at. Experience says we quite often get too many parameters. So how can we pick out what are the important things that we need to do with? And as a typical academic, I'll say there's lots more work to do. Please fund my research proposals. But no, it's becoming a far more important area, and of course not just in aviation, but across the whole engineering sphere. So hopefully you found that of some use. I think it tied in quite nicely with Peter and Simon's presentation. So happy to answer any questions on that or just join in general conversation. Okay, 17 minutes, not too far off. Thank you.
One comment on that list, like everything on that list, one that on there on the business point of view, what can I do about it? So if the mitigation is cheap, so cheap,
yes,
it's not the case, but if I can fix it by sticking a 50-kilogram weight on the bottom of the landing,
yes,
the direct, I don't care, certainly I'll just go for that. Drop down, take.
Yes, but your weight, but your aircraft design will say you don't want to put 50 kilograms of weight, do you?
If that's the risk mitigation, then it's kind of, okay, I can accept this.
Yes.
Aircraft's not great, you don't want it.
Right, no.
But it's not the case of Jimmy.
Sure.
But it's the kind of, if the solution is simple,
yes,
then it determines how much effort or importance on the uncertainty. If you can mitigate it simply, then you don't have to spend as much time.
But how certain is that decision?
Yeah.
Okay, right.
Yeah.
No, good point.